Hello, and welcome to the Water Research Foundation webcast on guidance on implementing an effective water loss control program, Project 4695. I'm Maureen Hodgins, and I'll be today's moderator. I'm going to go over some housekeeping, and then I'll introduce our speakers. You can download the presentation now. Just go to the event resources as shown here and select Presentation Download. And the slides and recording will be available on our website within 24 hours after the webcast, so you can listen to it again if you'd like. You can ask questions during the webinar via the Ask a Webinar area of your screen. Questions about difficulties connecting to the webcast will be answered right away. Questions for the speakers will be addressed at the end of the webinar. Or if we can't get to all of the questions, we'll follow up by email afterwards. Here's a screenshot of our website with the project landing page. You can download the 4695 guidance manual and Excel file now. They are posted on the website, waterrf.org, and they are free to the public. I also want to briefly tell you why WRF funded this project. The IWA, AWWA water loss control guidance and research has been out for about 10 years. So utilities have been learning and implementing practices to tackle water losses, and probably the easiest to recover water losses. So WRF decided to fund this project to discuss additional strategies and analysis beyond M36 in the current publications on water loss control. If your utility is a beginner at water loss control, then you may find that the guidance from AWWA M36 is sufficient. It suggests some initial water loss control program type steps. And this presentation today will talk about issues that you can consider for your future plans, and we'll just expand sort of your knowledge about things to consider in water loss control planning. If your utility was an early adopter of water loss control and you have 3 to 5 years of water audits, then this project will give you some concrete steps and processes and some research to help you make a water loss control plan. While the report is titled as guidance, it is more than a guidance manual. The appendices are filled with detailed information, so don't forget to check them out. And as a parting comment, water loss control is always evolving as we learn more. And I think a main point of water loss control and why it's important to utilities is that we want to make informed and cost-effective decisions for our ratepayers. I do want to mention 3 ongoing Water Research Foundation projects that are directly related to water loss control. The first project on the list is looking at smart water networks to manage pressure and flow to reduce water loss and reduce main breaks. The second project, and the first one, it just started, so it won't be completed until 2022. The second project is looking at using AMI data primarily for meter performance, and that should be completed next year. And the third project is looking at high-frequency meter reads, or really the water demand for non-residential buildings, large commercial, institutional, and large multifamily buildings, to get an idea of peak and non-peak demand so you can correctly size meters. Okay, now let's get to the main event. Here's our agenda, and I'll introduce our speakers. We have 3 speakers today. Chris Luber will start us off with a high-level overview of water loss control in North America since 1957 to today. Chris Luber is the past chair of the AWWA Water Loss Control Committee and has served on multiple project advisory committees for AWWA and WRF. Chris is the executive director of the Water and Wastewater Authority of Wilson County, Tennessee, and has over 36 years of experience in water loss control. Then we'll hear about the 4695 project from the lead researchers Gary Trackman and Alan Wyatt. Gary is a principal environmental engineer with Arcadis. Gary is very active with the AWWA Water Loss Control Committee and the AWWA Customer Metering Practices Committee. Gary, again, like Chris, has a lot of experience performing water audits, and assisted and recommended with the implementation of programs for reducing and managing non-revenue water. Gary was the principal investigator for the project that we'll be discussing today. Our third speaker is Alan Wyatt. Alan is a water utility specialist with 40 years of experience in utility performance assessment, non-revenue water, and operations and maintenance in the U.S. and in other countries. Alan has been very active with the non-revenue technical water community with AWWA and IWA. And as you see on the agenda, we'll close with 15 minutes for question and answer. And after the question and answer, if you could just hang on a second at the end, a 4-question survey will pop up, and we'd really appreciate it if you can take that. Okay, now I will turn it over to Chris Luber to talk to us about the water loss timeline.
Thanks, Maureen. It's my pleasure to participate in this webcast. Water Research Foundation has been a great resource for our utility. Now I'd like to take you through a timeline focused on documents and research I used as a utility manager to embrace the AWWA water audit methodology, which is the foundation of this research project. So back in 1957, AWWA came out with a committee report entitled Revenue Producing versus Unaccounted for Water. And it defined the metered water ratio, which was the amount of authorized consumption divided by water supplied, and it was expressed in a percentage format. The regulators took this and flipped it around and used the inverse of the metered water ratio and used the term unaccounted for water, basically trying to look at the inefficient operations within our utility. Nothing really happened in reference to the water auditing methodology for about 40 years. Then around the year 2000, the IWA and AWWA got together to devise a better best practice approach that would standardize the water audit methodology for utilities throughout the world and provide good terms and definitions and publish an array of performance indicators so we can break out the real losses, the physical losses, and the apparent non-physical losses on the system, and be able to use that information to compare performance from utility to utility and from year to year. 2001, AWWA funded the Beecher Policy Research Project and looked at state agencies across the United States which were using percent performance indicators. And this determined that they were not clear, concise, really were not operational for utilities to use, and basically determined that a better accountability system should be devised for the drinking water industry in North America. So in 2003, the AWWA Water Loss Control Committee put out a committee report, and in that committee report recommended the adoption of the IWA approach toward water accountability, and to discontinue the use of the term unaccounted for water, and not to use unaccounted for water as a way for target settings, and use other performance indicators, in this case such as like the ILI, which you'll hear about later on in the presentations. Then in 2006, the AWWA Water Loss Control Committee came up with the development of the AWWA Free Water Audit software. So now we have a tool, an Excel-based tool, to be able to report with the AWWA water audit methodology. 2007, the Research Foundation was involved in Project 2811. And my takeaway from this project really is that it concluded that the AWWA water balance is undertaken in a very standardized manner, and we can use this information to compare our performance from year to year and against other utilities. Also in 2007, another research project, 2928, was published and found that the methodology is very applicable for the management strategies throughout North America. And before we begin active leakage control, we need to do the water audit methodology first to break out the direction we need to go. 2009, the AWWA M36 manual, the third edition, came out, which defined how to use the AWWA water audit methodology. And again, recommended to no longer use the term accounting for water or unaccounted for water. 2010, the Water Loss Control Committee updated the software program to version 4.2. Then the regulatory environment got involved. 2011, Georgia came on board, required mandatory reporting with the AWWA methodology. 2012, the Delaware River Basin Commission Authority came on board, requiring mandatory reporting. And then here in Tennessee, 2013, the Tennessee Office of the Comptroller of the Treasury, who regulates us on a financial basis, required all utilities to report with this methodology. 2014, the water audit software was updated to version 5.0. Then in 2014, the Water Research Foundation Project 4372 developed some additional tools. And the real loss component analysis was developed, which is an Excel-based spreadsheet that then breaks out the real losses components and also provides an analysis of the economic intervention strategies. And another good tool here in this research project is the Leakage Repair Data Collection Guide. And it's a simple Excel spreadsheet, but it helps us to collect the leakage data that we need as utilities so we can forge the path forward. 2015, Project 4372 produced an analysis of over 4,500 water audits. So again, we're able to start looking at data, and data reported on a standardized format is very important as we compare our performance to other utilities in North America. 2015, still a lot of confusion out there. A lot of utilities and regulators using the term unaccounted for water. So at AWWA, we produced what we call the two-page flyer. And this flyer focused in on the recommendation that we focus in on the 3 V's, being the volume of the water supplied to the system, the volume of the lost water, and then the value of the lost water, and then also the validity or trustworthiness of the data and how it all interrelates. In 2016, the EPA gets involved, and they produced a document dealing with water conservation and alternatives to water supply expansions. This is a really good document that tied together water loss and how it relates to conservation and water supply. And the takeaway from this is they basically identified the water audit methodology as a best practice. 2016, the 4th edition M36 comes out, and a lot of good detailed information in the 4th edition that's dealing with the production meter testing. We know that the delivery amount is extremely important. If the amount of water delivered into the system is incorrect, all our other data is incorrect. Various descriptions on the software tools and some more examples on the regulatory environment. 2016, 4639 is produced, a guidance manual for Level 1 water audit validation. So Level 1 validation examines the inputs to improve the accuracy and document uncertainties. We have found that the water audit is more reliable with a Level 1 validation and really has now set an industry standard that before you start implementation strategies from the water audit, you really should seriously consider a Level 1 validation. Again, in the regulatory environment, California comes on board 2017, requiring the mandatory reporting with this methodology. 2019, we're seeing some policy updates. This one is from AWWA Metering and Accountability, where they were recommending annual water audits, but added some criteria in here that require the audits, requesting the audits meeting acceptable quality assurance standards, which I interpret that as basically a Level 1 validation. 2019, here we are with today's research project, 4695, and this is a guidance manual that's going to give you a playbook to help you with the strategies, the planning processes, and then the implementation activities. 2019, here we are again today, this year. The TEC from AWWA funded a project to look at the performance indicators. We've been using them for a number of years. Now we need to take a good look at, are there ones we need to phase out? Are there new ones we need to phase in based on the criteria? They need to be usable by the utility for target setting, for other stakeholders to understand, and even for the regulatory agencies to use if needed. This information then will be produced out into the industry through the AWWA Water Loss Control Committee. We have a task force called the Performance Indicator Task Force, and their intent is to produce a committee report, hopefully maybe sometime this summer, to provide the recommendations moving forward in reference to the performance indicators. And then out into the future, we envision an update to the AWWA Free Water Audit Software version 6.0, which will have multiple updates, but one obviously will be the inclusion of the new performance indicators. Just mentioned this project, WRF Project 4917. Maureen had mentioned it. I'm excited about this one. This is really exciting because it's moving us down that area of smart networks. And we know from work in the field, we're seeing pressure, transient type issues, and how we relate all that to smart networks to reduce water loss. And there'll be a number of case studies in this project. So from a utility perspective, just share a couple points. First, you must have buy-in from upper management. Well, I manage a smaller utility, so that's me. I am upper management, and obviously I've bought into it. Just want to share, though, as a utility manager, many things are out of sight, out of mind. You know, the tanks are full, none of the customers are complaining, everything's moving along. But remember, we're dealing with a buried infrastructure. It's not like potholes in a road, so we don't know what's going on underground. That's 3 foot or more buried infrastructure. So you've got to use the tools, the AWWA Free Water Audit Software, and use those performance indicators for target setting. Here we focus in on district metered areas. Our whole system has DMAs. We have 345 miles of water main. I come in the morning, and in 15 minutes I can scan my data and know if I've got any major leakage issues running in our system to reprioritize our crews. I've often said that the key to reducing real losses, leakage, is to reduce the runtime. I need to modify that statement now. It also needs to include reduction of the flow rate and the break frequency, and that's where pressure and transients from pressure come into play. That's the path forward. Regulatory perspective in Georgia, they do require level 1 validation, and they're coming from the water resources availability side. That's the driver. In North Georgia, they actually have target setting based on the real losses per connection per day. California requires level 1 validation, and they're focusing in on the operating pressure component and system-specific leakage targets derived from an economic model. So it's going to be really exciting to see what California comes out with within the next few months. Here in Tennessee, we're regulated by a financial regulator. They want to make sure we stay financially sound, and they're focused in on a data validity score, so we're to improve the accuracy of the data that's used in the water audit, and also on the value of the non-revenue water in comparison to the cost of operating the system, which today is the only financial performance indicator in the water audit software. And there's many other states and regulatory agencies that are also moving down a similar path. So the benefits for the authority here from WRF 4695. I got to say that, we've been very progressive here in reference to district metered areas and a lot of field work that we do. And us utilities can be innovative. We can do a lot of good stuff, but we don't do a good job of documenting our decision-making processes. So what's great about this project is through the participating utilities, the research team was able to capture that information and document how they made those decisions to go the right path. So you're going to have a playbook out there to use for whatever directions you want to go in the various activities in reference to non-revenue water. So I'm also excited because the report provides us with good validated data sets even by different regions in North America. So we can compare ourselves to other utilities that have validated information. And in this particular presentation, I'm going to be listening very close to Alan in reference to the AMI portion because that's where we're at today, the endpoints. We're looking at AMI and how to integrate that into the DMA work, and all this leading into the smart networks. So that completes my portion of the presentation, and Gary's up next and will present a high-level overview of the project, including the guidance manual content, implementation strategies, decision frameworks, and communicating the plan. Gary, take it away.
Thanks very much, Chris, and thank you all for your interest today. And before I zoom up to the 10,000-foot level to describe our project, I'd just like to acknowledge, and I'm not getting an advance here. Let's It is. There we go. I'd like to acknowledge our 8 participating utilities for sharing their insights and perspectives on their approach to water loss assessment, control planning, and implementation. Thanks also go to our principal investigator, Alan Wyatt, our research team subject matter experts, Stephen Davis and George Kunkel, and of course, our Research Foundation project manager, Maureen Hodgins. This effort also received timely and valuable support from our project advisory committee members, representing a broad spectrum of water industry perspectives, and we thank them for that. Our objective over the 18-month duration of the project was to create a guidance manual that North American water utilities may use to develop an actionable, cost-effective, and defensible water loss control plan. This plan will also be aligned with the utility's strategic goals and local circumstances and will reflect the experience of leading North American water utilities, large and small. While the sequence of steps in the planning cycle for a water loss control program shown here resembles the familiar plan, do, check approach, this guidance manual addresses specific needs identified by the project team, with concurrence by the project advisory committee. Additional guidance is provided for preparing an optimal apparent loss control element of a water loss control plan, identifying more meaningful performance targets, placing a financial value on the benefits of water loss control, assessing candidate interventions, selecting the most promising ones, and achieving targets, and assembling a financially attractive, multifaceted, optimal plan. Following an introductory section, the manual describes a process for defining a water utility's existing water loss situation and establishing a water loss control plan that recognizes the utility's strategic objectives, drivers, indicators, and targets for improving performance. Next, guidance is presented for identifying and screening candidate activities that address the key components of water loss. The implementation section features guidance for monitoring, tracking, documenting, and communicating results, costs, and benefits. 4 technical appendices include a worked example applying the situational assessment protocol, an expanded data set of water loss audit results useful for benchmarking, a sensitivity analysis of a pilot, optimal NRW model, and cost data for evaluation of water loss control activities. A 5th appendix contains a bibliography of numerous relevant references. Highlights of the core chapters of the guidance manual are the cohort-based criteria and approach to situational assessment, detailed action planning for apparent loss-related activities, financial analysis of pressure management projects where appropriate for reducing real losses, and implementation strategies for overcoming organizational barriers and communicating the water loss control plan. For a real-world perspective on water loss control, we requested detailed water loss control data derived from water loss audits from our participating utilities, together with responses to a series of questions on the topics shown here. For example, setting targets, evaluating candidate activities, allocating resources, documenting costs and benefits achieved, and future activities. The responses are summarized in the appropriate section of the guidance manual. An effectively managed water utility establishes core values with strategic goals and objectives that support its mission. As shown here, it's not difficult to connect non-revenue water management to these values, goals, and objectives. Teams responsible for achieving effective NRW management should consider these touch points when collaborating among department staff on related tasks and when assessing their performance. One or more drivers can influence a water utility's thinking when establishing a water loss control program. The drivers will typically require attention to one or both primary water loss components, apparent and or real. Note also that depending on the driver, Producing actionable information can be as important to the utility's customers as it can be to utility staff and management. Moving from left to right on this slide, regardless of regulatory requirements, the road to a successful water loss control plan begins with direction from utility management. Defining the current state of water loss performance is an essential first step that relies on sufficient data of high quality and long enough duration to discern trends in key performance indicators, or KPIs. Next, the NRW management team needs to identify potential water loss performance targets and candidate strategies for achieving them. The process for evaluating these strategies should include consideration of long-term factors such as distribution system asset condition and risk of failure, external and internal legal issues, technical elements, and service level considerations, and economic, social, and environmental factors. Implementation of the water loss control plan should also reflect staff organization and capabilities in the functional areas of finance and operations. External resources may be needed to fill the gaps, particularly in smaller systems. An initial period of implementation should be accompanied by performance monitoring and analysis so that adjustments can be made as needed to achieve the plan's objectives at least cost. Here we take a closer look at some external influences associated with utility, stakeholder, and regulatory perspectives that will be reflected in the water loss control plan, directly or indirectly. Addressing these influences effectively will further the utility's sustainability objectives. For example, customers are becoming more knowledgeable about the impacts of utility operations on their water bill and look to the utility to show that its actions are keeping rates affordable and that water supplies will be sustainable. Regarding oversight, an increasing number of state, provincial, and regional regulatory agencies are adopting robust protocols for reporting and managing NRW. Recent guidance at the federal level highlights the role of water loss control as an alternative to expansion of water supply capacity. In the financial context, bond rating agencies have established rationales and criteria for evaluating the operational effectiveness of a water utility, more recently including water loss performance. For privately owned water utilities, the Sustainability Accounting Standard Board has established criteria for the utility to document NRW performance that investors can reference when considering a potential investment. At the tactical level, the annual water loss audit using the AWWA Manual M36 methodology, informed by sufficiently valid data and a defensible valuation of the NRW volume, constitutes the foundation for an effective water loss control plan. Knowledge of present expenditures for NRW management will help a utility determine its economic levels of NRW and make the business case for activities whose monitored implementation will meet the established performance targets and achieve the plan's objectives. We've noted the importance of assembling a team that will own the water loss control program. Here we list the functional areas represented by the water loss management team that will most likely be involved with activities related to the 4 pillars for managing apparent losses to an economical level. A revenue water or water accountability person or group may be designated as the coordinator for the team's activity and have responsibility for reporting results to management. The activities range from keeping good records of active and inactive services, minimizing errors in the read-to-bill system, maintaining excellent customer meter accuracy, and minimizing unauthorized consumption. Similarly, implementation of activities related to the 4 pillars for managing real losses to an economical level will likely involve staff in the functional areas listed here. 3 of the 4 pillars of real loss management are often implementable in the short to medium term. These include improving response time for finding and fixing leaks, conducting forms of active leakage control such as conventional leak detection and correlation surveys, intrusive and non-intrusive acoustic sensing, and remote detection technologies. In some distribution systems or portions of systems, proactive pressure management may be found cost-effective while maintaining desired levels of service and water quality. The fourth pillar is a long-term asset management practice involving rehabilitation or replacement of mains, services, and appurtenances. Although not one of the four pillars of apparent or real loss management, accurate production or supply flow metering is a very important element of water accountability and is often addressed by the utility's internal SCADA and instrumentation and engineering groups, or with external assistance. We'll have more to say about this a bit later in the webcast. Determining your water utility's current water loss situation need not be a complex process. As shown here, the guidance manual presents 4 criteria for selecting one of 3 assessment protocol levels that best matches water loss audit data availability and quality based on the range or tier of the water loss audit data validity score and NRW management experience. Once volumes and valuations of NRW components are derived from validated water loss audits in step 1 of this 8-step protocol, the specifics of subsequent steps to be taken will depend on the utility's protocol level. In step 2, to detect changes in volumes and values of NRW over time and to spot data errors, utilities with beginner status will perform basic trend analysis on the primary NRW components, that is, total, apparent, and real losses. While intermediate and advanced utilities should be able to analyze trends in the subcomponents of apparent losses, in other words, customer meter inaccuracy, systematic data handling error, and unauthorized consumption, and real losses, such as leaks on mains, services, and appurtenances, and leaks from storage. In step 3, to apply principles of statistical confidence in the calculated NRW volumes and values, intermediate and advanced utilities will do well to perform an IWA uncertainty analysis. In step 4, benchmarking of a utility's current validated performance against that of other comparable utilities will be performed, with the depth of the comparison depending on the utility's designated assessment status. In steps 5 and 6, a utility will examine apparent and real losses in greater detail. In step 5, the beginner utility will perform a basic analysis of customer meter inaccuracy, while an intermediate and advanced utilities will review all components of apparent loss at a basic or detailed level. In step 6, the beginner utility will conduct a quadrant analysis, to be explained in detail later, at the entire system level of its real loss performance. In essence, this form of analysis enables a utility to gauge the potential benefit of implementing one or more types of intervention by plotting the infrastructure leakage index against a pressure management index, which Alan will describe later in the webcast. The intermediate and advanced utilities will also perform a leakage component analysis, or LCA, at the entire system level to ground truth the results of the top-down water loss audit. The advanced utility will carry out both the quadrant and LCA analyses at the pressure zone or district metered area level. The LCA includes a benefit cost evaluation of the 3 short to medium term real loss control interventions previously shown on the 4 pillars diagram. In step 7, a utility will review its existing water loss control practices, initially working off a checklist or assisted by the validity grading matrix included in AWWA's free water audit software. Intermediate and advanced utilities will progress to detailed evaluation of intervention methods and correlation with observed and documented performance. In step 8, depending on assessment protocol status, a utility will examine in varying degrees of detail the drivers and constraints that influence the content, pace, and expense of a water loss control program. This will enable the utility to develop a defensible, cost-effective, and successful plan for implementation. The guidance manual includes this decision tree framework at the programmatic level and 2 more at the component level for apparent and real losses. I'll not go through all of the steps here, but in essence, a utility should take appropriate steps to improve its data quality before making significant investments in water loss interventions. Initial steps would include activities to determine and minimize master supply meter error for its own sources and/or import and export water, and minimize read-to-bill errors, followed by some short-term activities to detect leakage. As data quality improves through improved data collection and verification practices, and the situational assessment of water loss performance becomes better defined, the utility would move toward the lower right side of this decision tree, planning interventions and then implementing them to address apparent loss and real loss control needs and meet performance targets over the longer term. This decision tree is focused on a key element of quantifying what is typically the largest component of apparent loss, customer meter inaccuracy. The process described here relies on a robust database of the utility's installed customer meter inventory. The objective of this process is to define customer meter inaccuracy for the purpose of entering a value in the top-down water loss audit. While best practice calls for a regular program of customer meter testing conducted internally or through contracted services, it is also possible to obtain a reasonably representative value for customer meter inaccuracy by applying the results of research conducted at Utah State University's Water Research Laboratory. Water Research Foundation Project 4028, completed in 2011, involved testing several types of in-service mechanical and positive displacement meters, ranging in size from 5/8 inch to 2 inch. Regression analysis developed a family of curves for meter accuracy based on cumulative volume, meter size, and type. The regression equations can be applied to the utility's comparably sized and typed meters, and together with an appropriate distribution of metered flows, a weighted average meter inaccuracy can be calculated. In turn, this calculated value can be combined with the weighted average inaccuracy for the utility's remaining meter sizes and types to produce a system-wide value to enter in the water loss audit. This decision tree is focused on guiding a utility through post-audit consideration of real loss interventions. Once the economic level of leakage has been determined and/or regulatory requirements for real loss reductions are known, priority areas within the distribution system should be identified based on leak break histories, and the utility should evaluate its staff capabilities for conducting candidate activities before moving forward. Candidate activities are those described in the 4 pillars diagram for real loss management, and selection for implementation is aided through the quadrant analysis noted earlier. An approach including pilot programs and associated monitoring of results is suggested before ramping up to full-scale implementation. No water loss control plan is complete without a communications plan. Effectively communicating your water loss control plan is vital for demonstrating good stewardship of water resources. Trending of key performance indicators that are readily understood by utility customers and stakeholders, as well as actionable by the utility's water loss control team, are essential for conveying progress. Buy-in from executive management, regulators, and stakeholders alike can be earned through periodic reporting of costs, benefits achieved, and program activities. At this time, I'll turn the presentation over to Alan Wyatt, who will go into more detail about the situational assessment protocol as applied to one of the participating utilities, the benchmarking database developed during this project, and guidance for evaluating apparent and real loss interventions. Then I'll return to describe coordination of this research project with the current program of related initiatives. These initiatives will produce more actionable key performance indicators for use by utilities and regulators as those regulatory programs continue to evolve. I'll also mention additional topics that would benefit from additional research. Over to you, Alan.
Thank you, Gary. Oh dear, I think I've jumped to the wrong spot. Sorry. Oh, pardon me. Well, thank you all for coming and joining in and listening with us. I'm happy to be here, and got a lot of data to go through, so I'll cover as best I can, but you can download the presentation, and as of yesterday, download the full report. Now, Gary went through the steps for the different levels of utilities for the 8-step situational assessment, and I'm going to use one of our participating utilities, Nashville, as a case example, and I'm only going to cover 6 or so of the steps just to give you a flavor of some of the highlights and somewhat new elements of the protocol. This first step, step 2 on trend analysis is just a very typical total bulk volume of real apparent, and the apparent's in green and orange for unbilled authorized. You can see a fairly steady profile and also a dominance of the blue real losses. This same type of trend can be done for unit volumes, values, unit values, etc. Gives you a feeling of where you are and how things have progressed. But it is important, in my opinion, that people understand the accuracy, or let's say on the other side of the coin, the uncertainty associated with the top-down audit. And this is a method that, as Gary mentioned, has been used by IWA and others in the States to estimate the error band or the confidence interval on the results of a top-down audit, either the apparent loss or the real loss. And it's a matter of having estimates of the confidence of the inputs, which in this table are shown in the light yellow. So how accurate do I think my length of mains number is, that kind of thing. And through statistical analysis, it tells you the resulting certainty, or let's say error band, associated with the result. And of course, on a top-down, we're most interested in the real loss volume. Well, in this year in Nashville, the estimate was 116 gallons per connection per day, but we see the range of uncertainty is up or down about 7%, that is from 107 to 122. Now that's a reasonably narrow window, and it's because of careful work on all of the measurements in the upper part of the water balance. But now when you step down into the value, the error or the confidence interval gets a little larger, such that the range of the value, annual value of real loss, ranges from 2 to 2.5 million. So that might give you a little pause in thinking about how much to spend on reducing that real loss. And so it's one thing to have a number, but it's another thing to have a number or a sense of sort of how much fuzziness there is in that number. The key element to reducing uncertainty, and Gary mentioned this, is improving your production metering, or if it's imported water, the master metering of that. And error cascades down from that initial confidence band. And so the message is get on that one. And the manual has material which is quite consistent with the M36 on methods for doing that. The next step that I want to highlight is benchmarking. And we have on the right some information from Nashville for apparent loss and its subcomponents over different years in gallons per connection per day. And then on the left, we have a benchmarking table. And this is derived from a data set that we put together under the project called WADI Plus. And I'll come back to describe it. But it shows the median, the 50th percentile of 68 utilities across the country over the last 8 years. And then the 25th percentile, that is the best 25%. And the higher percentile at 12 gallons is those who are the best 3/4 of all of the utilities. Now, if you look at Nashville just on apparent loss, you can see that they've gone down and down and down, getting closer to the median there of 7.6. And in fact, since we put this table together, the latest Nashville audit shows them at 7.1 overall apparent loss. So they've made, over the years, major progress and benchmark, pretty well. And we can take a deeper dive into this in step 5, and this is a longer time frame, again, looking at apparent loss. And what we have is, in orange, very small values for unauthorized consumption, almost unnoticeable values of the systematic data handling, and then large meters and small meters. And there's a massive reduction there, which can be attributed to a large meter testing and meter sizing and replacement program, followed by a small meter testing and replacement program. And one of the interesting little quirks here is that in these early years of 2000, 2001 and before, the utility did not own the commercial and industrial meters. The customer did. It's pretty rare, but the utility managed to get them back under their control, do the testing, a lot of work on right-sizing the meters and replacing if necessary, made huge, huge improvements in the apparent loss. So this is both an example of what's my status, how do I assess my position, but also what are the results of some interventions. There's kind of a crossover between those two. Now, if we move to continuing in Nashville to the real loss side, Nashville has had a outsourced leak detection program with utility repair crews following up for many years. And this graph here shows unreported leaks and breaks, the blue line being on mains and the purple on service connections. And it's descending down toward a value of 1, that is the ratio of the break rates or leak rates to the UARL leak or break rates. In other words, are you reaching that unavoidable break rate level? And the short answer is yes, they have made major improvements there. A similar graph, which I won't show you, shows the reported breaks, and they're all sitting down at about the UARL level. This leak detection and repair program has been pretty successful. You do notice in the last year an uptick in pressure there, the red line, and a decrease in ILI, and we're going to come back to why that happens. Now, this type of analysis can also be paired with what we call quadrant analysis, which Gary mentioned earlier. And there's 2 types of quadrants we present here, and they deal with the the four pillars of real loss. And excuse me, the first one is the what's called the modified Suez, and what we have in the x-axis is the break rate, which is sort of a proxy for your infrastructure or asset condition, and leakage. And Nashville is here with low reported main breaks, but relatively high losses. So that points you towards doing things other than asset replacement, but looking at pressure and improving quality and speed of leak detection and repairs. This is sort of a graphical component analysis similar to the LCA tool that's been mentioned. Now, if you set aside the asset management element and look at the other three pillars, this is what's called the Pearson-Troe quadrant, wherein you have ILI on the x-axis and a measure called PMI, Pressure Management Index, on the y. And basically, the Pressure Management Index is an index above a reference pressure that you wouldn't want to go below, like 50 pounds. So if you're at 100, your PMI is 2. Well, what this is telling you is if you have a very low ILI of 1 or something, but you have a high pressure management index, well, then you better get on the job of reducing pressure. Whereas if you're way over on the lower right corner of the graph, a high ILI and a low pressure management index, then your issue and strategic direction is on speed of leak detection and repair. And you can see Nashville is sort of in the middle there. Now, more investigation into Nashville's practices shows that the real areas of focus are on pressure and repairs on line connections. All right, I need to speed up a little bit. I mentioned the benchmarking database. This is called the WADI Plus that we developed, and we combined audits from a number of sources, principally the Water Loss Committee's WADI data set, along with a number of others, to have a broader database, more years, more locations, ended up with some over 200 audits and 68 utilities, sorted into regional cohorts. And I know it's hard to read, but there's a large number of indicators that are used. And here's just one example of a basic regional profile, the blue columns being the real loss and the green on top, the apparent in gallons per connection. And the percentiles, the 25th, 50th, that's the median, and the 75th. And you can see the old systems in the Northeast with older infrastructure tend to be higher. And anyway, this is just one little piece of what's in the WADI Plus database. Here's a screenshot of the South region, and it's defined in the document what is in the South region. And in fact, there is a spreadsheet on the WRF webpage that's downloadable where you can get each of these regional tables that show you the median, the 25th percentile, the minimum, the maximum, et cetera, for a whole group of indicators. On the right, there's a table that shows you, let's say, the medians and the 25th percentiles for all of the utilities in the data set. So we think this may be useful for assessing situations and ongoing benchmarking. Okay, we also looked at indicators that would work well or maybe not work so well for use in benchmarking and assessment. And there's a lot in the report in one of the annexes about this, but we're trying to find or single out indicators that aren't influenced by situational parameters very much, so they could be useful in comparing between utilities or over time. And some were stronger in that area than others. And an example here shows that ILI, commonly known, on its own does not correlate well with real loss volume unless you take into account the pressure at which that ILI was calculated. The upper right graph shows a metric of combining the ILI and the pressure, and you see a much tighter correlation to real loss. So bottom line, if you're going to use ILI, account for the pressure. Don't use ILI alone. Okay, I'm going to move now into target setting and planning. And the first step is to have a clear idea of the value. In other words, as Gary, my colleague Gary says, how much are the gallons worth? And the standard thinking, although this is still subject to some discussion, is the CRUC is the primary valuation basis of apparent loss, although handling sewer charges is important to be clear on and clearly labeled. On the real loss side, there's let's say, an array of factors that could be included. The baseline is commonly chemicals, electricity, purchased water, et cetera, but there are a number of additional avoided costs, which the manual describes, which can be added in, either short-run avoided costs or long-run avoided costs, such as the present value of future capacity expansions. So that would tend to increase the value of the real loss gallons. And once that type of valuation is settled or agreed upon within a utility or a state or whatever, then target setting can come in. And this slide shows an idealized approach, sort of pie in the sky perhaps, on target setting. You can see the main points. Real and apparent losses, considers the resources and capacity limitations, sets targets for normal and constrained situations, is not an enormous project with a huge data collection process, but gives locational specific targets. Now, again, it's ideal. I'm going to show you two concepts that work towards that. One is a cohort approach, which has been used in Georgia, Metro North Georgia. I won't go through all the details, but they defined it within that planning district in northern Georgia, found a median of 35 gallons per connection per day of real loss. So they defined a two-tier rule that those above 60 should get to 60 by the year 2025, and those between 60 and 35 should get down to 35, the median, by 2025. And that was become to be known as the drive to the median approach. This is not economic optimization, but it's a sort of first step type way of getting started. I put together this other table on cohorts where you have, for 2016 in Georgia, 9 different cells, or let's say cohorts, depending on 1, 2, 3 types of water sources and 1, 2, 3 sizes of utilities. And so you can look at the performance in each of these 9 cohorts and see how different utilities are doing. Some will be much higher than the median in that cohort, and some doing better, and then focus in on the ones that are most challenged, shall we say. We did also investigate a optimal NRW model, which I started working on some years ago. It comes close to the idealized approach. It does need a little more work on calibration of local cost curves due to limitations of available data, which we'll get into later, but it follows the typical graph you may have seen on economic level of leakage, ELL, with a total cost curve in black there reaching a minimum. But it has an additional element, which is the green line, which is the value of future capacity expansions. And if you're in a tight capacity situation, that green line will push upwards and in effect push the black line to the left, making a decrease in the optimal real loss. In other words, if you have a major water constraint, the optimal real loss will be lower. And you could plan for this. You could say, I expect a drought situation to reduce my source by so much, so I'm going to have a drought resilient target. This is an example of applying that method to two of our participating utilities, Nashville and Halifax. I've got to watch my time here, so I'm going to move quickly. But if you look at real loss, Halifax, which is well known for a very robust program, about 2/3 of the way down on the right, the real loss volume currently at 56, optimal at 53. So that's, close enough. It's within the error band of the model. But Nashville clearly has some reduction that it could benefit from and would pay for itself. And this is just a sample of what could be done with such a model. I don't want anybody to take this and go set targets for optimal apparent loss, but it shows how the optimal would change under different conditions as an illustration of the behavior of the model and how optimality should work. Okay. Now, as I said, this model is outlined as a demonstration of what a more ideal model could look like. It's not fully ready for prime time, so to speak, in that some more work is needed on the cost curves, but it gives people an understanding of how an optimal model could work and what kind of results could be obtained from it. All right, so that kind of wraps up the target setting end of things. And next we want to move into assessing interventions. And the first part to look at is the methods of assessing interventions. And there's two simple ones, sort of payback period and cost per 1,000 gallons of an intervention versus the value of the water. Those are fairly simple. And in the manual, we have examples of doing such analyses. You can see that on the right-hand side of the table there. And then there are three more sophisticated or complex analyses, which are to some extent related to each other, that dig in deeper. And again, we have examples of those in the manual. I'm going to show a couple of them here in upcoming slides. Before I get into that, I did want to point out that the participating utilities, and we've talked a lot about Nashville, about Halifax, but others have been good at using data, the FWAS water audit software, the leakage component analysis, to formulate their assessments and their planning. As a quick example, Albuquerque uses their GIS pipe map and their work order system to do like heat maps for where their leak detection crews should go and where their asset management activities should focus. I'm going to talk about Austin in a few minutes, so we'll come back to that. All right, so in the manual, we cover 6 types of interventions in the apparent loss control area. Meter testing, that's generally on the smaller meter side. Larger customer meter testing and replacement, which we touched on in Nashville. I'll give you some more information shortly. Small customer meter replacement programs. And then an example, which is actually a kind of a combination of static versus mechanical meters and business case for AMR, AMI. And then a thing in the manual on authorized consumption. We saw in Nashville that major reductions could be obtained, 75% reduction in apparent loss from large meter, particularly right sizing. And here's just 4 or 5 more places that have done this and found a nice boost to the cash register, so to speak. But it's important to emphasize that it's not just a matter of testing a meter, but ensuring that the meter is tuned to the demand profile. And demand profiles, particularly at large customers, can change over time. So that needs to be taken care to look at. Moving on now to AMR, AMI, I just want to quickly mention that the benefits from that type of system are not just on the apparent loss side, although certainly a major element is there, but there are benefits in combination with other tools and methods for the real loss side. Now, we wanted to recognize those, but the business case that I'll show you in a minute, does not account for these additional benefits, just to be a little on the conservative side. And basically, if you're going to compare an AMR system to a manual read system, you've got a great big trade-off between fixed cost and equipment cost. Labor cost is high on the manual read, and equipment cost is high on the AMI side. So what you need to do is a life cycle cost assessment that adds the initial costs and discounted values of the future costs to come up with a life cycle cost. And you see the manual is much higher in life cycle cost than the AMI. Steve Davis, who's an expert in this, did this analysis, and if there are any specific questions, I'm sure he could help on that. I don't have too much time left, so I'm going to whiz through some of this last piece rather quickly, but again, it's all found in the manual. The quadrants we talked about already. The leakage component analysis, many of you are familiar with. I'm going to give examples, and maybe I'll just do 2 or 3 of these on active leak detection, just DMAs, district meter areas, and pressure management. Can't cover everything. This is real data from one of our participating utilities, Austin, wherein they've had a contractor doing leak detection and calculated cost benefit by comparing the survey cost per 1,000 gallons recovered against what those gallons cost them at the minimal VPC level. And you can see a benefit cost ratio there on the right, lower right, of about 2. So it's paying for itself. Next slide shows pressure management. Again, I'm sorry to rush through this, but There aren't very many projects where we have solid information on costs, reduction in pressure, reduction in flow, real loss, burst rates, everything. But we've assembled 8 or so here, and we're working to get more of those on an informal basis. But your payback period is on the order of 3 years there, which can be quite attractive. Much less if there isn't much network reorganization. I think I'll cover this one and then jump a couple ahead. The DMA is a tool that's been growing a lot in the use in the U.S. and has been used for quite a while in Canada. And it's a sectioned off area of your network where through night flow you can achieve faster leak detection and localization. And it's most appropriate on smaller, less dense water systems where you have plastic mains such that acoustic methods don't work so well. And this is an example from one of our participating utilities, Consolidated Utility District in Rutherford County. And it's just a dramatic reduction in the real loss per gallon. And hats off to Kevin Hickerson and his colleagues there at Rutherford, because they've done a fantastic job. I do have a slide here on continuous acoustic monitoring. I won't go into it now, but this technology has really improved recently, and there are some good results coming from that. One last point, and then I'll close. One thing beyond looking at the economics of different interventions and the assessment and benchmarking is to numerical benchmarking, that is to bring the practices in, which practices are being used and which are not being used, and how does that show up in the audits, or does it? Are there practices you should be using? So this is an area of attention for us, both practices to improve the accuracy of the data you have, in this case, example, real loss, and then specific practices, which we've just been discussing on real loss. And there are some indicators that we can use to, for example, what percentage of your asset replacement or your assets are being replaced per year. So there are indicators that can be attached to these practices and used in combination with the assessment, benchmarking, and records of efficiency of interventions. So I think I should stop there and pass it back to Gary to look ahead a little bit more on other activities that are going on now and in the short-term future. Thank you very much.
Okay, Alan, thank you. Just to mention here, there's also a summary in the slide deck of the real loss practices of the participating utilities with information about the various interventions that they are presently employing or not, as the case may be. So I just wanted to close our webcast today with a couple of points about the context for this project related to other initiatives that Chris mentioned a while back. So the work products of this research project constitute a freestanding source of guidance for water utilities that want to determine their existing water loss performance, work toward establishing and achieving an economic level of non-revenue water, and effectively communicate their progress to stakeholders. As Chris noted earlier, there's a broader context for this work. This context reflects the interests of utility regulators, customers, and other stakeholders in having readily available information that promotes understanding of a utility's water loss performance relative to water resource sustainability, utility financial viability, and water service affordability. The AWWA Water Loss Control Committee's Performance Indicator Task Force is presently evaluating existing performance indicators including the suitability of percentage-based PIs, and where appropriate, we'll recommend additional PIs that meet the criteria of technical rigor, stakeholder understanding, use and target setting, progress monitoring, and NRW reduction, and compatibility with the state of readiness of utilities and the regulatory community to effectively employ them. These recommendations are expected to be publicized later in 2019 after a formal review by the WLCC membership and AWWA leadership. Utilities and stakeholders should also anticipate that an update to the free water audit software and a new system and model for capturing and sharing the increased volume of validated water loss performance data will be available in the not too distant future. As for where the science goes from here, this slide highlights a few areas for further investigation, the outcomes of which could yield significant advancements in water loss understanding, best practice, program implementation and communications, and additional benefits therefrom. For example, a closer look at the occurrence of pressure transients in distribution systems and their relationship to leakage would likely be useful for evaluating and implementing corrective actions. Additionally, articles and papers have been published on the water-energy nexus, particularly as it relates to the impacts of real water loss on a water utility's energy costs. It would be helpful if utilities would quantify and report out the benefits gained in reducing energy costs as a result of their reductions in real losses. We also continue to see new technologies evolve for customer metering, data analytics, and leakage detection that offer promising advances in water loss control. Results of pilot as well as full-scale applications of these technologies and approaches would certainly be of interest. While Project 4695 and the Water Loss Control Committee's initiatives described on the previous slide address some of these areas, our project team encourages the Water Research Foundation to support additional research in these areas. So on behalf of our presenters and research team, we thank you again for your interest in Project 4695. And now I'll toss it back to Maureen for our Q&A session and closing remarks.
Okay, great. Thanks so much, Gary, Chris, and Alan. A lot of information that gives us a lot of things to think about and putting it together in a different way than we've seen from some of the other reports. So we have a question and answer period now, and I did want to mention a couple announcements. I should have created a slide for this, but there is the North American Water Loss Conference will be in Nashville, Tennessee, December 3rd to the 5th, 2019. You can go to awwa.org to find out more about that event. And I also want to remind everyone, Gary, Alan, and Chris made some great slides with a lot of information that you could read after the webinar, and maybe you couldn't read all the text on it. You can download those slides now, and you can zoom in on those images and look them over. So you can download them under the resources on your screen. So now we've had some questions rolling in. I'm going to start us off with a question for Gary. Which performance indicators are considered most actionable? Or maybe Alan could answer that?
Well,
I was on mute. I was trying to answer.
Go ahead, Gary. Go ahead.
I'll start off, and Alan can weigh in. I was going to say that I think indicators of water loss audit data validity to start with, and these would be the individual component validity grades as well as the overall tier into which your data validity score falls into, are important because they point to the quality of your existing water loss practices that underlie the scores that you see in the water loss audit results. The second area is indicators that point to the component volumes of water loss, both apparent and real, expressed as gallons per connection per day. And also, and just as importantly, their value, either dollars per year or dollars per connection per year. But recognize these should be looked at on a system-specific basis. What one system does isn't always directly comparable to what your system does. And the third area, I think, is indicators that point to the types of interventions that are likely to produce positive results. So, for example, in the 4 pillars diagram for real loss control, we have an element that's related to improving the awareness, location, and response time, or repair time, as one important piece of information to track. Your leak break history, both in quantity and also geographically within your system. And then we pointed out the infrastructure leakage index and the pressure management index when you have a pretty good handle on what your average system operating pressure is. And then possibly relating that real loss in gallons per connection per day, normalizing that based on the average system operating pressure. Because we've seen some data suggesting that systems that operate at a relatively moderate average pressure are showing relatively high PSI-based unit real loss indicators. And this suggests that there may be some operational issues or perhaps asset condition issues that need to be addressed. So those are the 3 areas I would point to.
Okay, well, great, thanks. We have some other questions rolling in. There were 2 questions about small systems. And so the first one was any recommended cost-effective approach for assessing water losses in small systems, populations less than 500. And the second question on small systems was, do you think small systems would be able to use these processes fairly easily, or would it require a lot of training? Do you want to take a stab at that, Gary?
Yeah, I'll start off. I think, aside from addressing short-term needs like leak detection and master meter accuracy, it's critical for the small systems to really start collecting a sufficient amount of high-quality data, and they should rely on the M36 water audit methodology to help them do that. I think small systems with relatively large customers probably should take a look at the accuracy and the sizing practices for their larger customers, because that has potentially the greatest impact on their system revenue. And if they can recover some of that, then they can turn that money back into interventions needed to address real loss issues. And I think they can also look to technical assistance programs, even loans of leak detection equipment in some cases, and possibly even funding support from programs targeted to small systems out there. And these would be your rural water associations, your RCAP program, USDA, and there's some excellent guidance coming out of the Environmental Finance Center Network, as well as the regulatory agencies themselves. Maybe Chris would like to add some thoughts.
Yeah, I was going to say the same thing. Chris could maybe mention some of the work in Tennessee.
Yeah, sure. In Tennessee, I mean, all utilities of all sizes are reporting with the AWWA free water audit software. And actually, small systems, it works out real well because you don't have a lot of infrastructure out there. And I know, like within our utility, our DMAs are many of them only serving about 100 customers. So in reference to real losses, small systems are purchasing water, the cost of water supply is very high. And by setting up district metered areas and getting real-time flow and pressure data back, you're seeing events instantaneously, and they're reported to you, so you can go ahead and intervene and identify it. Very easy to increase the efficiencies within those smaller systems, and it's really not that costly.
Okay, thank you.
Sorry, can I just add this, Alan, that what I've found, and a lot of small systems or small utilities know their water distribution system very well. They know what pipe is where, and and a lot of, I hate to give a stereotype, but they kind of have this "let's get on with it and fix it" attitude, because that's my neighbor's water, and I don't think there's a heavy rocket science element to what we're proposing here. But what I've seen, and Chris can vouch for this, is that in places like Tennessee, if small systems can get together and talk, they can learn really well from each other and exchange ideas. And I think the National Rural Water Association can facilitate some of those kind of things. The Jeff Oxenford's group. I forget the name of that. You know, the protocol, for example, was tuned in a way that small systems should be able to handle it.
Okay, great. Well, thank you, Alan. We have another question. It came on earlier on when, Chris, you were touching on the different regulatory approaches that we're seeing. And you mentioned that California was taking, I think, you know, the driver was for water resources. But you also mentioned on the slide that California is focusing on an operating pressure component. So the question is, why are they doing that? And I think it might relate also to what Alan was talking about on slide 59 about the relationship between infrastructure leakage index and pressure. So Chris, did you want to take a stab at that?
Yeah, sure. My understanding in California is they're focusing in on the grading of the one input parameter for the average operating pressure of the system, and I believe they're driving utilities to seek a grade of 4. Which is basically the processes that are being used to collect pressure information. So they would be required to have some pressure loggers out, et cetera, to achieve such a grade. There's a direct relationship between operating pressure and leakage. Obviously, the higher pressures, the more leakage, and also the what we're finding out in reference to transients causing main breaks. So you're getting that increased frequency of main breaks if you get transients caused by pumps kicking on and off, or the fire hydrant, you know, being operated by the fire department and slam closed, things like that. So I think it's really more of a process of helping utilities to seek better information in calculating an average operating pressure. And when you do that and you start collecting more stuff on pressure, you start to see a lot of information in reference to what's really going on inside that pipe. Gary and Alan are both a little bit closer to the regulatory environment, so they may have additional information to add in reference to California.
Yeah, I was just gonna. I've been a little puzzled by the emphasis on pressure, but I have two thoughts. One is by pressure management and reduction, you can also achieve water conservation as well as real loss reduction. Maybe not an astounding amount of conservation, but you, to some extent, you know, hit two targets. So that may be part of it. But the other aspect is that pressures can be pretty high in many places in California, and they have a Danish association working with them, and a lot of the pressures in Europe are much, much lower than the U.S., so that may also be part of the concern on pressures.
Okay, great. Thank you. We have another question that's related about software. So and AMI and DMAs. What software vendors are capable of handling 50,000 plus meters for an AMI program with DMAs to give real-time data for water loss? And I'm not sure which one of you is...
Yeah, I'm not sure we want to get into talking about which software vendors. I mean, I don't really want to make any commercial recommendations, but
there's lots of possibilities out there, right?
Well, not lots, but one utility in the Southeast did an RFP for that kind of thing and got 3 pretty good bids, as I recall. And that, again, I don't want to...
Okay, point well taken. There are options, and we can follow up after the webinar with that person.
Yeah.
Okay, thank you, Alan. And there was another question. Do you think, this is kind of a big scale kind of question about utilities, do utilities have existing resources to devote to understanding and implementing valuable actions described in this research project? And I guess that's probably maybe best for Gary. He talked about how you get a plan implemented and create a team and line it up with your strategy.
Yeah, well, I think the easy answer is that some do and some don't. You know, we're hopeful that if they take a few moments and check out our guidance manual and for this project, as well as the work of others in Research Foundation reports and the M36 manual. There's quite a bit of material to draw from to develop an understanding of what the value of the losses are, and secondly, what the costs are associated with trying to recover them. And let's remember that not all of the losses are recoverable, so there's some economic level to work toward. But I think that the information in 4695 will be helpful in identifying what types of information are useful for the members of the team to collect and to analyze and begin to judge the cost effectiveness of different levels of implementation as they work toward achieving whatever targets they ultimately choose to work toward.
Can I just add to that?
Well, I was just going to, sorry, Alan, I'm going to wrap it up here. I wanted to thank all the speakers today and all the audience. We've come up to our time here. I really appreciate taking time out of your day to hear about this project, and please do download it. The resources are available now. And I also just wanted to remind you of the North American Water Loss Control Conference coming up in December, so look for that. So thanks again, everyone, and thank you for your time today.